We are going to begin this unit on reactions in aqueous solution by first talking about what a solution really is and a brief discussion of what the concept of solubility is all about. Solubility is something we'll talk about in a lot more detail later in the year when we discuss the concept of equilibrium. Here's a quick rundown of what we're going to be talking about today. We're going to start our discussion by discussing the solvation process itself. How do you go from a solid and a liquid into something that creates a homogeneous solution of itself? We've already defined what a lot of these terms are, but now we're going to talk about the process of how this happens. We'll then discuss the concept of electrolytes. We'll be identifying what an electrolyte versus a non-electrolyte is. We'll talk about solubility then next, the concept of solubility, the idea of saturation, and then finally some rules that allow you to determine whether certain salts will or will not be soluble in water. Once we have those rules under our belt and printed out, we'll then take a minute to practice and decide whether certain salts are soluble or non-soluble using the rules. Generally speaking, by itself, it's a very easy thing to do, but like in other chapters, this is something that's going to get a little more complex when we use it in conjuncture with other concepts. Okay, so let's start by talking about the solvation process itself. Well, solvation is the process of a solute becoming dissolved into a solvent. And this is the creation of a homogeneous solution. We have two different items that are coming together to make one singular item, which is the solution itself. It's important to remind you that the process of dissolving something is a physical change. A lot of the stuff we're about to see is going to look very chemical, but there's still a physical change. The actual chemicals themselves are not being altered. Something we'll talk about in the next unit is that this process also involves heat being absorbed or given off in the process. Sometimes dissolving things is going to make your solution feel hot. Sometimes dissolving things is going to make your solution feel cold. A great example would be putting salt on the roadways in the wintertime. Most people already know that salt changes the freezing point of that liquid, and as a result it prevents ice from forming. But what a lot of people don't also realize is that when the salt dissolves in the water on the road, it also gives off heat, helping the salt or helping the ice and the snow to be melted as well. So you kind of get a double effect there. But as I said, this is something when we talk about heat energy, it's something we'll talk about in our next unit. Now let's take a look at the solvation process itself, and we'll have an actual model here of some molecules to show you what really goes on in this process. On the left here we have a beaker depicting a sugar water solution, and over here we have a zoomed in picture. This stuff right here would be our sugar. And these individual spheres represent the individual sugar molecules. Now the sugar is placed inside a beaker containing water, and these little molecules here are going to represent our water molecules. Now it's important to notice that some of these water molecules have little symbols on them. They have these little delta minuses and delta positives. That's telling us that the hydrogen side of these water molecules has a positive charge, and the negative side has, or the oxygen side has a negative charge. We'll talk later in the year about what the deltas are there for, but for now it's just reminding you the fact that water is polar, and a lot of times it's this polar characteristic that allows water to dissolve certain substances. Anyway, in the process of solvation itself, what basically happens is individual sugar molecules like this one get broken off by the water molecules. You can imagine these charges as attaching onto the molecule and kind of pulling them away from the rest of its friends. And then once it gets pulled away, what happens is these individual sugar molecules, these solute molecules, get encapsulated or surrounded by a circle of water molecules. And you can almost see how the solvation process works. What was once just a piece of sugar is now a sugar encapsulated in a bubble of water. This kind of gives you an idea when you look into a sugar solution, you don't see the sugar molecules or the sugar grains anymore. All you see is the shell of water around them. As a result, we see something that appears homogeneous to us. When all of these sugar molecules dissolve, the end result will be all of them are encapsulated by water molecules such as this, and as a result we'll have finished the solvation process. This process occurs a little differently depending on whether you're dealing with covalent substances or ionic substances. With covalent substances, that solvation occurs by encapsulation of the solute molecules entirely, and again, as we just showed in the previous picture, you get this shell of water molecules surrounding them. But the important thing is that the entire molecule gets surrounded with the water molecules. When you're dealing with ionic compounds, something a little bit different happens. Because those water molecules have a charge, the first thing that occurs is the separation of the positive and negative ions. What was once NaCl when it goes into solution, becomes sodium plus ions and chlorine minus ions. They're no longer together. And then the individual ions themselves get encapsulated by the water molecules. So you get this separation thing. So again, the big things to think about here is when you're dealing with covalent, it's whole molecules. When you're dealing with ionic, it's this idea of separate ions. And that's going to be something that's important for us later in this video, and something that's definitely important for us later on when we talk about certain reactions that happen in solution. Before we move on, let's talk about a couple quick definitions. These are not things that show up too often in the process of what we do, but it would be remiss to go past this idea without taking a second to talk about these ideas. The first of all, it basically is the idea of being an electrolyte versus a non-electrolyte. Now, before we start, we have to point out the fact that both of these guys represent water-soluble substances. You can have electrolytes dissolved in water, and you can have non-electrolytes dissolved in water. The difference is what happens after they dissolve. An electrolyte is a solute that creates a solution that conducts electricity, and a non-electrolyte is a solute that does not conduct electricity. And that's the real big difference here. And the difference comes up in the fact that electrolytes are made up of ionic solvents, and non-electrolytes are made up of covalent solvents. We'll talk in a minute why the ionic versus covalent makes a big difference. Now, this is a term you've probably heard before, this idea of electrolytes. It's something that athletes hear a lot, and the reason being is electrolytes are a very important component of your body. As you lose fluids during exercise or sports, you're losing water. You're losing the water that your body needs, but you're also losing electrolytes in the process. Your brain works by conducting electricity throughout your body. Without a sufficient number of electrolytes in your body, you lose that ability to conduct electricity, and you lose the ability to communicate with muscles properly. As a result, sports drinks, such as this guy over here, Gatorade, not only contain water in them, but they also do a lot of advertising talking about the fact that they contain significant electrolytes. For example, sodium ions is something that you'll get a lot of, and potassium ion, I believe, is another one you'll get a lot of in a drink like this. Adding more of these ions back into your body would not only, like I said, rehydrate you, but allow your brain to effectively communicate with the muscles around it. Now, we can see this concept of electrolytes versus non-electrolytes in a lab that we actually did earlier in the year. If you recall, we did a lab where we talked about the differences between ionic and covalent compounds, and we talked about the fact that ionic compounds conduct electricity, and as a result, when I make a solution with ionic compounds, this would be a solution that causes the light bulb when placed into it to light. This would represent a solution made with an electrolyte. Here we see the light bulb does not light. Even though we created a solution, that's telling us that this stuff is a non-electrolyte. And as a result, it does not conduct electricity. We define these in terms of ionic versus covalent, but in actuality, we can also define it as being electrolyte versus non-electrolyte. Now we see we got this third light bulb over here, and based on what I can see, we can see that this third light bulb is dimly lit, which means it's somewhere in between what we got here with electrolyte and non-electrolyte. The question is what's making up this solution that seems to be in the middle? Before we get into the explanation of that dimly lit light bulb, let's talk about why this process actually works. Now, earlier in the slideshow, I showed you a non-electrolyte, sugar, which is covalent, dissolving in water. Now I'm going to show you an electrolyte, in this case NaCl, dissolving in water. Over here on the left, we have our solid sodium chloride reacting with our liquid water, and as a result, we're creating the aqueous solution of sodium chloride in water, or salt water. As we can see from before, the particles from our original substance are now encapsulated, but instead of an NaCl being encapsulated, it's the chlorine ions being encapsulated and the sodium ions being encapsulated. Now, because these individually encapsulated pieces have charges, that allows electricity to travel through it. If you recall, electricity is made up of flowing electrons. This is something you should have learned last year from your physics class. And electrons, just like our charged particles, have charges. This allows these electrons to basically hop from one charged particle to the next, and as a result pass through the solution until they get to some sort of electrode on the other side. So it's the charges in our electrolytes that allow these charged particles, these electrons, to travel through them. Like I said, if electrons can get through, that means electrical charge is getting through, and that's the flow of electricity. Here we have our non-electrolyte solution again, our sugar water, and here we have our electron again trying to get through, but notice here, no charges. We'll put little ends in here to represent that they're neutral. There's nowhere for our electron to attach onto, and as a result we get no flow of electricity here. This is a solution where our light bulb in this case won't light up. Now here's our last piece on the differentiation between electrolytes and non-electrolytes, and we're going to discuss why that light bulb on the end from the previous was able to light dimly but not as bright as the other one. And we can define electrolytes as being strong electrolytes versus weak electrolytes. So a strong electrolyte is when in solution all ionic compounds separate into ions which are then encapsulated in water. So basically you get full separation. That's another way of thinking of this. Full separation. Every single molecule of your compound separates into its individual ions. Conversely, we can also have weak electrolytes. A weak electrolyte is when in solution, some of your ionic compounds separate and some stay whole. So in this situation, we only get partial separation. Some of your ions separate into positives and negatives, but some of them stay as the whole group. In both cases, this doesn't affect solubility. Both substances, strong electrolytes and weak electrolytes, can dissolve very easily in water. It just depends on what you get when you actually dissolve. Now, if you think about this in terms of conducting electricity, in this situation with a strong electrolyte, you're going to have lots of ions. And as a result of having lots of ions, we would expect good electrical conductivity. In this situation, only some of your atoms separate, or your compounds separate, and as a result, you're going to get fewer ions in solution. Some of those ions don't go into solution, they stay as whole compounds and they're encapsulated as such. As a result of that, we're going to get less conductivity, and this is going to be our dim light bulb. Whereas up here, we would expect to get a very bright light bulb. Let's move into our last idea of this process, and that's finally the idea of solubility. I find this is a word that most people have a pretty decent idea of what it means, but let's put some definitions to it anyway. Solubility is basically the ability to dissolve a certain solute in a certain solvent. Basically, does salt dissolve in this particular solvent, or does salt not? If it does, we would describe it as being soluble. If it doesn't, we would describe it as being insoluble. Another way of putting this is the ability of solvent molecules to encapsulate those solute molecules. We describe the solvation process as that encapsulation. If water doesn't have the ability to encapsulate a particular solvent or a solute, then as a result we would not expect that stuff to dissolve. It would have no or very low solubility. And as we've already alluded to a couple times now, this solubility is dependent on the characteristics of the solvent and the solute molecules themselves. If you change the solvent, we would expect our solubility to change, and if you change the solute, we would also expect our solubility to change. A great example, table salt in vegetable oil, nothing happens. The salt and oil combination doesn't allow the solvent and the solute to interact in a way that dissolving or solubility will occur. Whereas table salt and water, we all well know that that does occur. And again, it's the interaction between the solute and the solvent that allows that encapsulation to happen and allows solvation to occur. Now, when you're talking about things dissolving in solution, you have to talk about the idea of saturation. Basically, the idea of how much solute can be dissolved. And again, this is an interaction between the characteristics of the solute and the characteristics of solvent. Some solutes dissolve tons in certain solvents, and other solutes dissolve very, very poorly, and depends on that interaction. So just to get that down on paper then, all solvent-solute combinations have a maximum amount of solute that they can hold per unit solvent. And that's something we'll talk about in terms of the idea of saturation. This concept of saturation, just before we move on, is often temperature dependent as well. This is something we'll talk about in a few minutes when we talk about the idea of supersaturation. So we can describe solutions in three different ways in terms of saturation. The first and easiest one to talk about is the idea of a saturated solution. This means you've dissolved the maximum amount of solute per unit solvent. You can imagine having a can of water in front of you and adding in table salt and adding in table salt. Eventually you would hit a point where no more table salt can be dissolved, and that's when you've reached the saturation point of salt in water. If you were to try to add more salt or more of your solute, you would find that that salt would remain undissolved. It would just fall to the bottom of the container, and no amount of stirring would get that salt to dissolve. On the opposite end of the spectrum, we can talk about an unsaturated solution. This means you have dissolved less than the maximum amount of solvent possible. You can imagine then if you were to add more solutes, because you haven't reached the maximum, because you haven't reached saturation, that solute would then dissolve, and it would dissolve more and more and more until eventually you got back to the thing we talked about first, which is that saturation point. You've saturated your solution. Logically speaking, these are the only two options that should be available. However, there is a third case, and that's going to tie back to that temperature discussion we had a little bit earlier. You can have a supersaturated solution. In a supersaturated solution, you have now dissolved more than the maximum amount of solute possible, which sounds ridiculous. Why do you have a maximum if it's possible to dissolve more than that maximum? Well, it's very important to notice that this idea of saturation, as we mentioned before, is temperature dependent, meaning as the temperature changes, the saturation point changes. And typically, most solutions increase their saturation point as temperature increases, which means the saturation point gets higher as the temperature goes up as well. So to get a supersaturated solution, we raise the temperature of our solution, we dissolve more solute in at that new temperature, and then we allow it to cool back down again. When it cools back down, the extra solute will actually stay in solution. It needs to get pushed out of solution somehow, and just cooling down isn't enough for that to occur. As a result, you get a situation where you have a supersaturated solution, and as you might imagine, this is actually a relatively unstable scenario. Supersaturated solutions have been used in a couple of different ways, and at the very least can be a very interesting thing to watch. And this brings us finally to our last concept that we're going to be talking about today, and it's the idea of solubility rules. Ultimately, in this chapter, you want to be able to look at a solute-solvent combination and decide whether or not the solute is going to be soluble in the solvent. And that's exactly what these rules are about. It's rules for determining which ionic compounds will or will not dissolve in water. We could have solubility rules for any solvent, but since water is our most common one, that's the one I'm going to hold you guys responsible for. The rules themselves use grouping in categories to classify millions of compounds as being soluble or insoluble. So we can have a very small number of rules and apply them to a very large number of compounds, whether they will or will not dissolve in water. The alternative would simply be to memorize the solubility of every individual compound and or look it up every time you need it. Clearly, though, I would like to think that having a small set of rules that we can use over and over again is clearly a much better situation than trying to do any type of memorization or have to be forced to look things up over and over again. That all being said, we use tables such as these in order to determine the solubility of certain salts in water. And these are two different formats showing exactly the same thing. They just organize the information differently. In this table, we organize things by whether they're soluble or insoluble. Everything on the first half of the chart represents soluble solutions. Everything on the second half of the chart represents insoluble. And over here on the left side of the table, we have exceptions. So these are the rules, and these are the handful of compounds that are exceptions to that rule. Over here, we have the same exact information, but in this case, it's now organized by ion. So you have nitrates, you have acetates, you have the halides here, you have sulfates, carbonates, and phosphates, and it organizes it this way. Again, and over here, we have the general rule and the exceptions as well. Same information, two different ways. Your job right now is to make sure you have at least one of these two charts somewhere in your notes, as we're going to be using this in class as a tool to help us identify the solubility of pretty much any substance we come across. This will be useful in a few minutes, and it'll also be very important later on down the road when we start talking about precipitation reactions. So, stop the video, find this on the bottom of the page, download one of these two charts, if not both of them, have them available and ready to go. Now here's the kind of things that I expect you guys to be able to do. You should be able to look at a compound, such as these guys listed here, and decide whether these guys are or are not soluble in water. Well, we're going to use that chart we had from before, and we'll take a look at this one first to do it as an example, and then I'll leave the rest for you guys to try on your own. So we've got sodium nitrate over here. The idea is to think about this in terms of the two ions that are present, and decide from those two ions on our table whether or not they are soluble or insoluble. Well, our two ions in this case are sodium ions and nitrate ions. Let's go back to our table and take a look and see what the rules are going to tell us how to handle this. Well, looking over on the table on the left here, I see nitrate first thing on the list. And they talk about nitrate as being in the soluble group, so nitrates are soluble. Now we always got to check, are there any exceptions? And it's telling us that there are no exceptions, meaning that all compounds containing the nitrate ion are soluble in water. If we go back then to our compound over here, sodium nitrate, it contains the nitrate ion, so we describe this substance as being soluble. This would definitely dissolve in water. I want you to repeat that process of looking up the individual ions, comparing it back to the table, and see if you can define the rest of these as being soluble or insoluble. So here's some of the results we have from the soluble-insoluble practice problems. We already defined the sodium nitrate as being soluble. That one was a piece of cake. Here we have lithium sulfate, which separates into lithium ions and sulfate ions. If you look back on your chart, sulfate is listed there as being soluble. There are a couple exceptions, but one of them is not lithium, which means this substance would indeed be soluble. Again, we go to our sulfates again. This guy is made up of barium and sulfate, and it tells us that sulfates are indeed soluble, except barium sulfate is one of our exceptions. Sulfates paired with bariums end up being insoluble, so this stuff would not dissolve in water. We keep the process going. We have this list of phosphates here. This guy is made up of potassium ions and phosphate ions. It tells us that phosphate ions are insoluble in water, except for phosphate ions containing the potassium ion. That makes this substance soluble. If we continue the process here, in this case we have scandium and we have phosphate. Just as we already said, phosphate ions are insoluble except for a couple exceptions. In this case, scandium is not one of those exceptions, so we would describe this stuff as being insoluble. And then finally, our last example. We see that this guy is made up of iron ions and chlorine ions. We look up halides, which is chlorine, fluorine, and iodine, and we see that these guys are typically soluble with a couple exceptions. Iron is not one of those exceptions. Therefore, we describe this stuff as being soluble in water. Hopefully what you can see is that these rules are relatively straightforward and easy to use, and more than anything it's a process of becoming just familiar with them a little bit. And that'll happen definitely through some practice problems in class and some homework that you can work on individually. As always, if you have any questions, please feel free to bring them up in class, and hopefully either through the work that you're doing with your group or individually, or through the questions that get answered with me, this is something that can get cleared up.